All right, welcome everybody, and thank you so much for joining us today. My name is Simon Reuning, and I'll be the host for our new podcast, Ask Why. Today we have Alexander Nabel with us here. He's the EMEA Technical Marketing Manager, and he has a very interesting topic that he's going to talk about, and it's going to be the influence of ESR and ripple current.
Yeah, hello Simon, and thank you for having me here today.
So Alex, to find the right capacitor, all you really need to do is understand the capacitance and the voltage, right?
Well, it depends. It might be a sufficient statement for some DC current applications, but certainly not for AC applications.
So what is the challenge in AC applications?
Well, for any AC application, regardless of the frequency and the shape of the curve, also the maximum ripple current of the capacitor must be considered.
So do I need to find the ripple current on the data sheet?
Yes, but this is only a typical value at one dedicated point. Unfortunately, the maximum ripple current rating is not a constant. It depends on the application frequency and the ambient temperature. This is the reason why the maximum ripple current cannot be stated easily in the datasheet.
What exactly does the ripple current depend on?
Well, one factor is the thermal resistance of the capacitor. The thermal resistance, RTH, is depending on the construction method, like the leads of the capacitor, the contacts, the electrodes, also the product size and the cooling capability of the case and the dielectric plays a huge role. And consequently, the used capacitor technology is the first main factor to consider when choosing the best fitting solution. Each capacitor technology has different construction and has therefore different ripple current capability behavior. Especially for film capacitors and aluminum capacitors, the self-heating is an important topic as too high temperatures may decrease the maximum lifetime. As always, the rule is the same here. A capacitor, like any passive component, should never be used outside its specification.
Well, that sounds like many things I need to be considering when choosing a capacitor.
Right, and unfortunately, there's even more to consider that besides the component characteristics, also the ambient temperature, the PCB characteristics, the circuit design, the pads, the trace thickness, and even more. They all have an influence on the thermal behavior of the component.
So let's go ahead and talk about what YAGEO Group has to offer.
Yeah, as you may know, our four main capacitor technologies are ceramic, tantalum, film, and aluminum capacitors.
What about supercapacitors?
Right, we can consider this as a different capacitor technology, but as the applications for supercapacitors are totally different and supercapacitors are never used in AC applications, we do not need to take them into consideration. So let's focus on our four technologies, and I would like to start with a brief overview about the multi-layer ceramic capacitors, because they have a very simple construction where the main part, the body, is the dielectric ceramic material with the electrode layers inside. So the body is the ceramic material without any additional elements such as housing, pins, or resin. And this simple construction can handle high temperatures, up to more than 200 degrees if needed. But in general, we are talking about 125 up to 155 degrees. Nevertheless, for resonant applications like WPT or LLC, our MLCCs heat up and the designer may experience overheating and not properly designing the network. Therefore, we do recommend a safe zone for the temperature rise, which is minimum 20 degrees above the ambient. And you can see this in the picture here, where we see the temperature rise versus the ripple current. The example is for a class 2 dielectric X7R versus the class 1 COG dielectric. So the thermal resistance changes when using different class dielectric, as well as the DC bias is different for class 1 and class 2. The next technology is the aluminum electrolytic capacitors. They are polar and thus have a lower ripple current capability. And depending on the configuration of capacitor, the used electrolyte and construction of the capacitor, the RTH and the delta T and the ESR vary from technology and series. Well, typically we know all the most used technology is the wet electrolyte. And they have some challenges to be considered regarding higher temperatures. But now the latest technology is to use a polymer instead of wet electrolyte, or a combination of both, polymer hybrid type. So using polymer or polymer hybrid instead of wet electrolyte reduces the ESR of the aluminum capacitor over the frequency and over the temperature. Thus, the self-heating of the component is reduced up to 50% and makes them ideal for higher ripple current applications. The next technology is the film capacitor technology. They are available in two main different construction types, either in metallized film technology, where the film is the dielectric, or a combination of a film as dielectric and two additional aluminum foils as electrodes. And the main reason for the usage of film technology is the higher current capability. But nevertheless, the level of ripple current capability depends also on the used film material. So the construction of the film capacitor with plastic, box, film, foil, resin, all this influences also the self-heating of the capacitor, which can be somehow be a limitation of the technology. Last but not least, the fourth technology, our tantalum capacitor, they are polarized. They are ultra stable, small size SMD products. They have a good ripple current capability. The new polymer tantalum technology is having a better properties than the older manganese dioxide technology. Tantalum capacitors with low or very low ESR values are going down to 4 milliohms, and they enable ripple currents up to 8 amps per part. But we need to keep in mind that the limitation of this technology is the low voltage range up to 75 volt currently.
I mean, that's a lot of technologies for me to consider. How do I find the right capacitor for my application or for my customer?
Yes, that's a good question. So to answer this question, let's have first a look on the screen. So we see here the existing voltage and capacitance range for each of the four technologies. As an example, if the application voltage is 1000 volt, we have no choice within the tantalum technology, and also aluminum capacitors are limited depending on the series to 450 volt, 630, or maybe some series go up to 800 volts.
And then the MLCCs, are they limited to the maximum capacitance range around 22 microfarad and maybe 33 microfarad?
Correct. But do not forget that there's always another option to put several capacitors either in parallel to increase the capacitance or in series to increase the voltage.
So is it possible for us to actually reach higher values outside of those bubbles?
Yes, for sure. But putting multiple capacitors in series and in parallel will also increase the needed board space and for sure the cost.
So I remember in the beginning of the presentation, you talked about not only to consider voltage and current for your capacitance. Do you have any comparison sheet for that?
Yes, correctly. And this table we see here is digging deeper and compare the four capacitor technologies with their features and benefits, and the maximum available values at YAGEO Group. So the main advantages of each series is highlighted in green. For example, you can see that the MLCCs offer a very high voltage range up to, depending on the series or the size, 10,000 volt. Well, sometimes there's limitations up to 3 kV or 6 kV. The second step, we can also consider the needed capacitance value. And here you see, okay, the aluminum capacitor, which is marked in green, offers the highest capacitance range in the series ALS7. So here you can have a first start and you see also the maximum temperature and the maximum ripple current per piece and the maximum ripple current per volume, which gives you the next indicator of which product might be the best for my solution.
So what about cost? I know that customers always have that question come up. What is the best cost factor for me to pick the technology?
Well, we cannot compare that very easy. Because, yeah, for sure, one MLCC is always cheaper than one film capacitor. But if we take the example we just had, and the customer needs high capacitance value of maybe 100 microfarad or even higher, then maybe he would need 10 or 20 MLCCs, and they are most likely more expensive than one single film capacitor. So here we have a more general overview with the highlights for each technology, which shows exactly if the customer needs high ripple current, then it might be sufficient to use ceramic capacitors or film capacitors. If you need high capacitance range and cost-efficient items, then you would need aluminum capacitors. And last but not least, if he has no problems with high voltage range, he's below 50 volts, and just needs a good ripple current capability, he can even use tantalum capacitors.
Now, with all these considerations that I have to take for this type of technology, is there any type of tools or any support that we can offer for our designers that are working on new applications?
Yeah, sure. And the first start is the datasheet. As you mentioned at the beginning, if there is the indicator of the ESR and the ripple current in the datasheet, yes, it is. This is just one example series where we show the ESR, which is stated at a certain frequency, like here 100 Hertz. So this is just one point on the graph, but it's easy to compare this series with another series. A deeper view we can have with our online tool. So this allows to compare capacitor technologies more in detail. So we see here a screenshot. And in this example, the blue curves represent a ceramic capacitor and the yellow curves represent a film capacitor, both with somehow similar values. The main advantage is that we can see the ESR over different frequencies, which is not stated in the datasheet. And so we can see in this graph, the ESR and therefore the ripple current of the film solution is higher.
Right, so this is actually a very easy tool for somebody to use and find out exactly what the maximum ESR and what the maximum ripple current of their products are.
Yes, exactly. And we recommend always to start with our simulation tool on our webpage. So let's come now to the conclusion, and I hope this helps everyone to understand how to find the right capacitor. Because this finding the best solution requires ideally to consider all technologies, not just one technology. And we need to compare each solution regarding the ESR, the maximum current, the number of needed pieces, if there are needed more than one, but also the needed space on the PCB, and last but not least, the cost of the final solution. So with our simulation tools on YAGEOgroup.com, we have a very high level solution, which is effectively assists designers to evaluate the component behavior and the features of the individual capacitor technology at various operation conditions, and thus assist with the selection of best fits capacitor. And everyone who takes some time to find the best solution will ideally save money and space, which are the most important things to lead the own projects to success.
All right, well, thank you, Alex. This was very informative. And if you guys have any questions on the topic that we discussed today, you can always feel free to reach out to us. And with that, I just look forward to seeing you guys next week for our next session. And with that, just remember to ask why.